In the last slide, we saw the conditions of contact separating force and the contact penetration that are required to be satisfied to have a realistic contact simulation. The contact algorithms in ANSYS that are used to ensure these conditions in a contact pair are listed in the table below. Contact algorithm options in ANSYS are 1. MPC or multi-point constraints, 2. Penalty method, 3. Normal Lagrange method, and 4. Augmented Lagrange method. First is MPC, or multi-point constraint. This algorithm simply creates the constraint equations between the nodes of the contact and the target pair. This is the simplest method to solve a contact problem. This requires a linear solution. However, only bonded or no separation contacts can be modeled using the MPC method. No complex contact outputs, like penetration, force, or the frictional stress, will be calculated. Second is the penalty method. Penalty method creates a contact separating force proportional to the penetration at the contact interface. This is a relatively complex method and requires a nonlinear solution. Penalty method calculates all the complex contact outputs, like penetration, pressure, friction, etc. Contact problems are often easy to solve using the penalty method. The main problem with the penalty method is the penetrations are often high. Therefore, it is generally not recommended when local contact results, like contact pressure, are important. Third is the normal Lagrange method. This method enforces a zero penetration condition. Therefore, penetrations predicted at the contact interface are negligibly small. This ensures accurate results at the contact location. However, because of the zero penetration condition enforced, contact solutions are often difficult to converge. The fourth and the default ANSYS contact algorithm is Augmented Lagrange method. Augmented Lagrange method introduces additional factor to the penalty method. This limits the contact penetrations. Series of iterations are carried out to ensure that the penetrations are limited. This is the most recommended contact algorithm. However, in many contact problems, it will give same results as that of the penalty method. Therefore, careful results review is required when local contact results, like contact pressure, are critical. In the last slide, we have seen the overview of the ANSYS contact algorithms. Now, we are going to see the details of the penalty method. We have already seen the contact penetration condition, that is, the gap G should greater than or equals 0, where G equals delta minus nu C minus nu T. Penalty method introduces a penalty function phi n to the contact pair. The penalty function can be defined as phi n equal to into brackets minus G plus modulus of G whole divided by 2. The contact separating force is calculated as lambda n equal to Kn multiplied by phi n, where Kn is the contact stiffness. it can be noted that, when contact gap G is positive, the penalty function phi n is 0. When it is negative, the separating force is equal to the penetration times the contact stiffness. Thus, separating force reduces the penetration. Note that, in order to have a zero penetration, contact stiffness Kn should be infinite. As it is not possible, penalty method will always allow some penetration in the contact pair. Normal Lagrange method enforces a zero penetration condition. This condition can be enforced using the following relation: into bracket G plus lambda divided by K, bracket multiplied by lambda, equal to 0, where K is the contact stiffness. When gap G is positive, separating force lambda has to be 0 to meet this condition. When the gap is negative, an appropriate separating force is generated. Note that zero penetration, or G equal to 0, is possible with the finite values of K. Even considering the numerical limitations, a near zero penetration is always maintained in the contact pair. Now, we are going to see the augmented Lagrange method. This is just an improvement to the penalty method to limit the penetration. Lambda n is equal to Kn multiplied by phi n plus psi. Or, in other words, lambda n minus psi equal to Kn times phi n, where Kn is the contact stiffness, phi n is the penalty function, and psi is the augmented parameter. Note that in this case, a zero penetration condition can be achieved with finite values of Kn.